So the plan here for today, we'll start with some questions from, homeworks and whatnots. So if you guys, hi Alex, do you guys have anything from homeworks or the packet that I gave you guys or whatever else? Happy to go and hit some questions here real quick.
Could you do 15 from like 5.3?
5.3, number 15?
Yeah.
Sure.
Did you see the picture?
All right, so number 15 from 5.3, the directions say use part 1 of the fundamental theorem of calculus to derive or to find the derivative of the function. So we're looking at this. So we're going to do the derivative of the integral from 0 to tan x of square root t plus square root t dt. So I know that the derivative is going to cancel out the integral, and I can replace the t's then in my formula with whatever the variable is there. So I'm going to have tan of x plus square root tan x. But I also have times the derivative of tan x, because it's like a chain rule thing going on here.
Yeah, so why?
Yeah, so the fundamental theorem of calculus part 1 says, like, okay, we have some function g of x, which is equal to like f of t dt, right? So what I'm doing then in this problem is I have like g of tan of x, right? So when I take the derivative of this, that's a composition. So I have a chain rule. Exactly right. Does that feel good? So whenever this, whenever that bound is not an x, not just a single variable, there's a chain rule piece that happens at the end.
So even what if it's just x? There's no x.
Well, then it's times the derivative of x, which is 1, which is like whatever, right?
It's like x squared plus 1.
Yes, then you'd have a times 2x at the end. Yes, exactly right. So all we need to do then is to take the derivative of tangent, which is secant squared. Again, you guys should still have those memorized. They're going to come back in a big way real quick. And that should be our final answer. Does that feel okay, Nate?
Yeah, I just...
Yeah, the chain rule piece, yep. No problem, though, right?
Pretty much just if you have, it's really one thing.
The integral symbol, yep.
Yeah, and then you have something like tan x in there.
Yeah, so like on this one, you do your derivative. So you'd replace those z's with square root x's, and then you'd have times the derivative of the square root x at the end. And you have to do that derivative and simplify some stuff. But like, that's the gist of it. Does that feel okay?
Yeah.
Okay. Paulo.
Can you do 17?
17? Sure. Yes. Yeah, go ahead. So I have the integral from 1 minus 3x to 1 of u cubed over 1 plus u squared du. So the first thing that I want to do is I notice my bounds are the opposite of what they're stated in the fundamental theorem of calculus when my constant is on top and my variable is on bottom. So I'm going to use my property of integrals. So I'll make that negative to swap the bounds. Now if I take the derivative, I'm going to go ahead and replace my u's with that 1 minus 3x. And then I have times the derivative of that 1 minus 3x. And then from there, it's just kind of simplifying some stuff out. So this is the derivative of 1 minus 3x is just negative 3. So I can do that. And I don't know if the back of the book answer, if they did more simplifying than this, if they foiled this all out and tried to reduce things or not, but this would be fine for me.
Yeah, I messed up. I meant set, sorry.
Oh.
It's fine. It was 17 for the second.
Oh, from 5-2?
I didn't realize myself.
That's okay. We can look at that one. Okay. So this is going to be 5.2, number 17. Okay. So it says to express the limit as a definite integral on the given interval. Okay. So if we're going from, yeah, okay. So if we're going from 2 to 6, that's going to be the bounds of my integral, right? And this guy here looks like my function. And then this piece just will become the dx. And that should be all you need to do. Is that what the back of the book said, Paulo? No. What is the back of the book? Well, let me look. I got it over here. Oh my goodness, thank you.
It says -9.
It said it was -9? That seems weird. Charlie, I have an early dismissal. And Addie, this is your day to get the Spring Arbor mail. Yeah. You and Maria can be roommates. All right, let me look at this real quick here. Paulo. Try to see what they're driving at. Okay, when I look at the back of the book, it has exactly what I've written down.
Oh, okay.
So I don't know, maybe we looked at the wrong problem or something,
Yeah.
or we're in the wrong section, I don't know, but
That still makes sense.
yeah. So it makes me feel a lot better. It's like, oh, -9. I'm like, how in the world were they? Okay, well, anyway. Sure, no problem. Alex, are you? Okay, just messing. Got it. Any other questions from homeworks? Yeah, Elena, sorry. 5.2, number 29. Sure. Okay. So this direction says to express the limit, or express the integral as the limit of Riemann sums. So I know in general, that's what I'm trying to get to, right? Okay. And I know that delta x is equal to b minus a over n. So in this case, that's going to be 6 minus 2 over n, or 4 over n. Does that feel okay? And I know that xi is going to be a plus delta x times I. So that's going to be 2 plus 4i over n. And that should be everything. And then let's just write down what our f of x is. Is going to be x over 1 plus x to the 5th. Does that feel okay? All right, so now we're going to just kind of combine all these ingredients together. So we have f of xi. So everywhere there's an x, I'm going to put in my expression for xi. Oops, I don't need the f there. And then I have times my delta x. Oops, and I did that wrong down there, right? Should be 2 plus xi squared. And then I don't know if the back of the book did some fancy simplifying to like FOIL some stuff out and like clear those fractions inside of fractions in there. Let's look up and see what the answer is and see if this is just like equivalent to it. 5.2, this is number 27, right? 29. Okay. Oops. No I there. But no, they didn't do anything fancy. They just left it with what I have here. So this would be done. You're dying to ask a question right now. Go ahead. Alex. So on a test, the only thing I'd be asking you to do is to go back and forth between this form and the integral. So like this kind of a problem, it would likely be a multiple choice style question, in which case then it's just like the question of how much simplifying do I need to do? Well, enough to know, so you know which one to pick, would be my answer to that. Does that feel okay? So I wouldn't ask you to do this by like free response, but this is certainly a reasonable multiple choice style question, in which case then like how much simplifying do I need to do is obvious because it's enough to get to whatever the answer is there, but probably not much. I would expect nothing past this. Does that feel okay? Very good. Anybody else? Alrighty. Well, let's do 5.4. So in 5.4, we're going to introduce the concept of the indefinite integral. So we now are going to have two types of integrals. There's the definite integral that we've been working with so far, where it has bounds, and the indefinite integral where there is no bounds written. So the definite integral is just a number, right? The fundamental theorem of calculus part 2 tells us how to compute that number. That's the antiderivative evaluated at b minus the antiderivative evaluated at a. The definite integral is just a number. The indefinite integral is a function. It is the general antiderivative. So that's what all of this is just kind of saying. We've talked about how to find antiderivatives previously, right? So again, this is just our definite integral from the fundamental theorem of calculus. So our antiderivative, or our indefinite integral says the integral of f of x dx is the antiderivative of f of x. And that's the gist of it. So we'll present to you guys this table of integral rules. Do any of these integral rules look familiar? What are these rules? They are the derivative rules in reverse, right? They are ostensibly the derivative rules in reverse, right? I know the derivative of the natural log is 1 over x. The integral of 1 over x is the natural log, right? So these are, although it looks like, oh my God, I just got dumped a million formulas that you're telling me I need to memorize. You already have them memorized. They're just the derivative rules, the opposite direction. Is everybody okay with this? So again, it's doing antiderivatives. We've already done that a little bit in first semester. This is just formalizing it. So from here on, we're just going to do a boatload of these examples where we're going to be mixing all these antiderivative rules together into single problems. Sound good? Okay. So our first example, we have the integral of 10x to the fourth minus 2 times secant squared x. So the first thing I'm going to do is use my properties of integrals to distribute the integral through and pull the constants out front of my integral symbols. Is everybody okay with what I've done here? Does this remind you of something? Just like how we would have approached this as a derivative, right? We differentiate things term by term. We ignore the constants out front, right? All right. So what is the antiderivative of x to the fourth? X to the fifth over 5. Very good. What's the derivative of secant, or the antiderivative of secant squared? Tangent. And then we need one other thing here. Plus c. Will I mark you down if you forget your plus c's when you're doing an indefinite integral? Yes. Will the AP mark you down if you forget the plus c? Yes. Is it that important, Mr. Kulik? Yes. All right, so we could do a little bit of light cleanup here, and 10 divided by 5 is 2. And we could do that. Does that feel okay? That would be our final answer. Let's look at the next one. As this is currently written, do we have a antiderivative rule to deal with this? We do not. We don't have anything to deal with the quotient at all, right? What should we do instead? I am going to take this trig expression and I'm going to think about it as that and that's what I'm really going to be integrating, because that does look like something I have an antiderivative formula for, right? If I go back and look, cosecant times cotangent, negative cosecant x, right? So just like we saw for derivatives, oftentimes there's going to be some simplification you can do beforehand to make the problem much easier. You could do this problem as it's currently written, but not yet. Like, it's possible to do it without doing the trigonometric substitution, but this is by far the easier way of doing it. Eventually we'll get the tools so that you could do that problem. We don't have them yet. So far, so good? Okay. Next one, it says evaluate the integral from 0 to 3 of x cubed minus 6x. What do you notice here? Yeah, this is a definite integral, right? Because it has the bounds on it. But really, I approach this the same way. I'm going to go ahead and start by using my properties of integrals to kind of distribute things through. So the antiderivative of x cubed the antiderivative of x and I'm going to just kind of loop these guys together. Is everybody okay with what I did there? So I'm going to end up with 3 to the 4th, which is 81 over 4, minus 27. And if I make a common denominator there, that is 108. So I end up with negative 27 over 4, I think. Yes, Finn. So if you were given this question on a test, technically this, I guess this would be fine, but like, you know, if it's multiple choice, that's not going to be what the answer looks like. I want to remind you guys that for these definite integrals, these are all checkable with our calculator as well. So to do this on my calculator, I'll press the math button. I'll go down to command number 9 on my calculator called fnint. And then I can just type this in exactly like it looks like on my sheet of paper. And notice that that is the same thing as negative 27 over 4. So far, so good. I want to point out to you that you could use, if you're careful, you could use this also as a checker for your indefinite integrals. So for example, if I say if I did this one, I wasn't sure if I did this correctly. Want to make sure I'm in radian mode here. But if I did the integral, I'll just do it, say from 0 to 1 of cosine theta over sine theta squared, d theta is going to give me an answer here, hopefully. Oh, maybe 0 is a bad choice. Sure was. I broke my calculator. Why is 0 going to be a bad choice? Because I can get that's where like all the asymptotes and stuff are all at. Let's go from 1 to 2. That was a poor choice on my part. Stay away from 0 when you're doing trig things. So there's that. Now let's say my antiderivative was this. So this would be negative 1 over sine of 2, and then minus a negative, so plus 1 over sine 1. Got the same result, so I should feel pretty good about this. So you can, even on an indefinite integral, if you have your calculator, you can use it as a checker if you're not quite sure if you did that right. You guys see how I used it as a checker? Okay. All right, let's go on and look at this. So again, if I'm going to do this, I would start by using my properties of integrals. Oops. Forgot some dx's. Okay, so the antiderivative of x cubed, we just did that a moment ago. The antiderivative of x, well, we did that earlier also. What's the antiderivative of 1 over x squared plus 1? Tan inverse. I heard somebody say that is correct. Again, if you're not up to speed still on those derivative, and in this case antiderivative rules, go back to the flashcards that I made on the, what's the flashcard thing called? Quizlet. Go back to the Quizlet that we saw from semester 1 and run through that, refreshing your memories. So this is going to be, I'll simplify here and just make that 1/2, 2 to the 4th minus 0 to the 4th. And then we'll do that, and we'll have 2 squared minus 0 squared. And then we'll have that, and it'll be tan inverse of 2 minus tan inverse of 0. I don't know what tan inverse of 2 is off the top of my head, but I know tan inverse of 0 is 0. Everybody's okay with that? And then I can simplify that down. I'm going to leave that, since at this point, with this guy in here, it's a calculator problem, right? There's no way to do tan inverse of 2 by hand. All right, what if we look at here example 5? This one is still doable with all the rules that we have, but not as it's currently written, because we have this quotient in here, and it's not one of the ones we have an antiderivative rule for. So when you see something like this, you should think, well, maybe I can simplify this first. How could I simplify this? So the fraction is the issue, right? So what I would do is I would just rewrite this as 3 fractions. Oops, I wrote 2t down there. With a common denominator. Everybody okay with that? Now I can reduce each one of these 3 fractions. And that is now something that I can integrate, right? So the integral of 2 is 2x. The integral of the square root of t is t to the 3, well, it's 2t to the 3 halves over 3. And the integral of t to the negative 2 is going to be negative 1 times or plus t, or 1 over t, or t to the negative 1. And then we're evaluating from 1 to 9. Notice here that I'm just like condensing my work, right? I still did the same thing, I'm just not showing as much. But you can clearly see each antiderivative. So I have 2 times 9 plus 2 times 9 to the 3 halves over 3 plus 1 over 9 minus 2 times 1 minus 2 times 1 to the 3 halves over 3 minus 1 over 1. And then it's just grinding that out. Is everybody okay with how I did that? Notice that it didn't make any difference if I thought about it this way, where I found each antiderivative and then looked at the difference of the whole thing evaluated at 9 minus the whole thing evaluated at 1, or like we did on the previous problem, where I looked at the difference of each part of my antiderivative. Whatever's more convenient for you, whatever feels easier for you is fine. Okay? So you can experiment with trying to do it both ways and how you like to do the evaluation. Sometimes, like, if it's 0, it's much easier one way than another way. Like if one of the bounds is 0, that's usually pretty nice. Okay. So a little application here. So part 2 of the fundamental theorem of calculus says that if f is continuous on the interval or the closed interval from a to b, then the integral from a to b of f of x is equal to f of the antiderivative of f valued at b minus the antiderivative of f valued at a. Or in other words, I can rewrite f of x as just the derivative of cap f. Right? Means the same thing. We know that the derivative of capital F represents the rate of change for y equals f of x, right? That's what a derivative is a rate of change. So f of b minus f of a is the change in y as x changes from a to b. So with making that small reformulation, this is essentially still just a fundamental theorem of calculus part 2, but we call this, so what this allows us to do is it gets like, if I take the integral of a rate of change, the result is the net change. So again, thinking about the integral as an accumulation function, right? If our function is like a constant function of 55 miles an hour, we're traveling our car, and we travel for 3 hours, the integral of 55 from 0 to 3 is just going to be 3 times 55, which is exactly how much distance we've accumulated in driving our car for those 3 hours. This is exactly that same idea. Okay. So, example 6. It says a particle moves along a line so that its velocity at time t is v of t equals t squared minus t minus 6, measured in meters per second. Find the displacement of the particle during the time period from 1 to 4. And then find the distance traveled during this time period. So what's the difference between displacement and distance traveled? Yeah, so imagine you're at your house. You leave your house, you walk around the block and end up back at your house, right? What's the displacement? 0. What's the distance traveled? Well, like 4 blocks, right? Whatever the distance was to walk around the block. So mathematically, displacement is going to be just the integral. The distance, the total distance traveled is going to be the absolute value. So for us, that's kind of what matters. Is everybody okay? So that's an important distinction to remember. Displacement is just the plane integral. Distance total is going to be the absolute value. Now, sometimes they could be the same thing, right? If we're walking in a straight line, that's going to be the same thing, right? Displacement is going to equal the distance traveled, but it doesn't have to. All right, so let's go and look at this problem then. So for part A, we're just going to do this integral. So that's fairly easy. Everybody okay there? So what do we get? We have 63 thirds minus 16 halves plus 1 half, so that's minus 15 halves. And then negative 20, so that'll be negative 18. And then we'll need to make a common denominator there, so that's going to be 6. So 126 over 6 minus 45 over 6 minus 114 over 6. So we have this guy and this guy leave us with 12 over 6. So that's going to be negative 33 over 6, which I guess reduces down to negative 11 over 2, or negative 5.5, I think. Oh my God, it's doing this again. The book says it's supposed to be negative 4.5, so I lost something somewhere. What did I lose? I must have done some multiplication wrong somewhere. Where was it? Who sees it? $16 plus 1 is that. That's 64 minus 1, so that's that. 24 minus 6 is that. Okay. Oh, I bet it's here. 6 times 18, is that not 114?
No, it's 101.
Ah, there we go. There it is. There's my missing parts. There we go. So that's going to leave me with 14 left, right? No, 18 left. Goodness gracious. Arithmetic is hard in the morning, guys. So that's going to be minus 27, and I reduce that down. That'll be, there we go. Well, at least none of the calculus was wrong. Just my mental math. Woo! All right. And this would be meters, right? Yes. Mm-hmm. All right. So if I'm doing this, and I suppose I have to do this by hand, obviously if I have my calculator, I could type it into my calculator and just say, calculator, do this. How do I do this without the calculator? Yeah, I have to break this up, right? So I think probably for this one, thinking about what the graph of t squared minus t minus 6 looks like. What are the x-intercepts for this going to be? Positive 3 and negative 2, right? And it's going to open up like this, correct? So I need from 1 to 3, I need like the negative of this because it's all below the x-axis there. And then from 3 to 4, it's good the way it is, right? Does everybody feel okay there? And how I decided to break that apart and why I needed to break it apart? I think doing that previous example, the last class, really helped give you guys some intuition as to what to do here exactly. Finding that point, though, where if you need it, not every time will you need it, but if you need to break it, where to break it. Here's the beautiful part, though. Guess what we've already done? We already did the antiderivatives here, right? That is terrible today. I am ready to... Does someone have a baseball bat laying around? Because I think it's clobbering time here. Does that feel good as to what to do from here? Can I just stop instead of grinding through all the plugging in? It's not really that exciting. You get about 10.17 meters or 61 over 6. I'll put that down there. pretend like we did and I didn't just look at the answer. There's just going to be a lot of arithmetic and like, yuck, right? If I have to do it by hand, I can. I just don't want to. And you don't want to watch me like grind through fractions and stuff right now, I'm assuming. It's not very exciting. You're like, none of it's been exciting, Mr. Kulik. And I would be like, you know what? Like, have a better attitude. All right. So this last example, figure 4 shows the power consumption in the city of San Francisco for a day in September. P is measured in megawatts. T is measured in hours. Starting at midnight, estimate the energy usage for that day. What would I want to do here? Yeah, you know what I would do? Yeah, exactly. I'd just find the area under the curve. You know, like, okay, well, that's 400 times 24, right? And then that's like whatever times what, you know, so I'm just like, I'm just going to do like one of these guys. That's close enough. And then I'll add up whatever's left, you know, what those full boxes are, and then whatever the leftovers are. I'll just make an estimate like, you know, this one's maybe like 2/3. That one's maybe like a quarter. That one's negligible to the point I don't care. Maybe that's a half. Maybe that's a half. Maybe that's a half. Maybe that's a half. That one I don't care about. That's maybe a third, maybe 2/3, maybe a half, you know, etc. I'm just going to kind of like tally the stuff up that way is what I would do. You could also approximate it using like a midpoint Riemann sum or something if you wanted to. Not wrong to do that. But given there's a grid on there, I'm just counting boxes really. You know what I mean? Does that feel okay? And I don't want to count up all those boxes. I could if I wanted to, but like, it just means me typing stuff into a calculator and being like, plus 1/3, plus 2/3, plus 1/4, you know, like, and just annoying. I'm not doing that stuff by hand, nor would I expect you to. That's it. That's all I have for 5-4. So I want to point out too, I have the test 5. I think this is, at least tentatively right now, this is the format and the outline. So part 1, I have 7 multiple choice questions and 1 free response, similar to those 5.3 practice FRQs that I gave you guys. Part 3 is the calculator section. I have 3 multiple choices here. I have 7 integral problems. So like definite, indefinite, absolute value, piecewise, U sub we haven't talked about yet. And all that stuff just all mixed together, like do the integral of this. And then 1 FRQ that's kind of like a Riemann sum style. And I put in some more practice MCQs and FRQs. Somehow I had 2 sets of MCQs for this chapter that seemed like they were mostly different. So I don't know which one I meant to do. So I put them both in there. You'll probably find at least some problems overlap because when I looked at stuff, I'm like, oh, that's a good one. I probably thought it was a good one both times. Do you want to take a look at the FRQ practices that I gave you guys last time and do one of those here together? Do another one of those, guys? Does that sound good? All right. Get your packets out. I'm going to skip down and maybe do the last one, you know, just on the hope that probably most of us haven't gotten that far yet. Jenny. Yeah, I have extra sitting on top of the file cabinet there, so feel free to grab one. I think that's where I left them. If they're not there, then holler at me, but I thought I put a stack up there. You're welcome. Good. I'm glad they were there. All right. So number 7 here reads, the continuous function f is defined on the interval from -5 to 8. The graph of f, which consists of 4 line segments, is shown in the figure above. Let g be the function given by g of x equals 2x plus the integral from -2 to x of f of t dt. We're first asked to find g of 0 and g of -5. So g of 0 is going to be 2 times 0 plus the integral from -2 to 0 of f of t dt. Everybody feel good there? So this integral is all formatted the way we'd like it. So I'm just going to be looking for the area from -2 up to 0. What shape is that? Trapezoid. What's the area formula for a trapezoid? Yeah, 1/2 base 1 time plus base 2 times the height. So base 1 is like that distance, so 2. Base 2 is going to be that distance, so 1, and the height is 2. So we have then 3 is what we get. Everybody feel good there? G of -5 is going to be 2 times -5 plus the integral from -2 to -5 f of t dt. It's going to be -10, but what do you notice about the bounds down here? Yeah, they're backwards, so let's flip those. To flip them, what needs to happen? Yeah, the integral becomes negated. So now we're just looking from -5 to -2. So we're looking at that triangle and that triangle. So that first triangle, the area is 1/2 base, which is 3 from -5 to -2, and its height is -4, right? Because its height is really f of -5. And then plus 1/2. The other triangle, my base is wait a minute here. My base of that triangle isn't 3, is it? It's 2, right? 1, 2. Goodness, great googly moogly. The base of my other triangle is 1, and its height is 2. So that becomes -4 plus 1. So this inside becomes -3. So -7 minus -3 is, I'm sorry, -10 minus -3 is -7. Just check my worked out solution real quick because there, okay, good. It's early, you know. Arithmetic is hard sometimes. Oops, that was all part A. Any questions so far? Feels pretty good? Okay. Part B says find G prime in terms of f of x. Okay. So G prime of x is going to be the derivative of 2x plus the integral from negative 2 to x, f of x, or f of t dt. So when I do the derivative of 2x, I get 2, and the derivative of the integral from negative 2 to x of f of t dt is f of x, right? Again, remember the variable name changes to whatever's in the integral. Does that feel good? And don't worry about the chain rule here because the bound is x and the derivative of x is just 1, right? That's why I'm not worrying about a chain rule here. All right, then it says for each g double prime of 4 and g double prime of negative 2, find the value or state that it does not exist. Okay, well, I'm going to need g double prime then. So the derivative, or g double prime, is the derivative of g prime. So that's just going to be f prime, right? So g double prime of 4 is going to be f prime of 4. So if I go up and I look at this guy and I locate 4, 1, 2, 3, 4 looks like it's here. So f prime of 4 is going to be the slope of that line at x equals 4. So I can just do rise over run there. So I have like negative 3 minus 3 over, what was it, 8 minus 2. So that comes out to be negative 1. And then the other one was g double prime of negative 2. So that's going to be f prime of negative 2. And if I go look at f prime of negative 2, that's here. What's the derivative going to be there? Good, doesn't exist. Why? Because it's a corner. Okay, good. Great job, guys. On what intervals, if any, is g concave down? So if we're concave down, that tells me the second derivative is negative. Yes?
Say on the AP, like part B had like multiple parts to it. If you got one part wrong, would you just like not pay any points for that?
No, they would have had milestones in terms of like, oh, if you've done this, that's a point. If you've done this, that'd be that was probably a 3-point question, maybe more. So yeah, there's certainly like multiple points available inside of these FRQs for each letter A and B. Typically, sometimes they can be just 1-point problems. If it, like if part A was just asked you for like g of negative 5, I'd expect that to be a 1 point. Is that?
Yeah.
Okay. Yep. Good question. So when the second derivative, or when g double prime, we know is the same as f double prime. So now we're just looking for where f is decreasing. So if I go back to my graph, what intervals is f decreasing on? Well, this one from negative 2 to 0, and this one from 2 to 8. So I just said, because that's where f is decreasing. So I just read it from the graph. Nothing more to show there. It says give reasons for your answer. So I would say that string of what I wrote there, that g being concave down is equivalent to g double prime less than 0, which is equivalent to f prime less than 0, and then stating that that's my interval because that's where f is decreasing. I think is an excellent explanation. I think that any grader would have no problem with what you wrote there or what we wrote there. Then D says the function h is given by g of x cubed plus 1. Find h prime of 1. Show the work that leads to your answer. Okay. So I would start here. So let's do the derivative of h. That's going to be g prime of x cubed plus 1 times the derivative of x cubed plus 1. So that. Is everybody okay there? Now, we've done g prime already, right? Notice that we wrote that down. So, oops, thought I changed my pen back. So that's going to be 2 plus f of x cubed plus 1. Is everybody okay there? So there was a chain rule here when I did this derivative. So I had the derivative of the inside times the derivative of the outside. Sorry, the derivative of the outside times the derivative of the inside. Does that feel good, Finn? Yeah. Okay. So now that we have an expression for h prime, I can go and plug in h prime of 1. And f of 2, I can just read from the graph, which is 3. So I get 15. That felt okay? So again, you will have an FRQ on your test that I'm going to give you, very much in the similar style of these FRQs on this packet. If you've gone through and done any more than the first couple, you'll see that they're kind of all the same. But I think they're really good practice. This is a very common AP format question where it really tests if you understand your fundamental theorem of calculus and can use it, to do a problem like this. Like integrate things geometrically. It checks if you can know how to do that. Like it checks if you understand the fundamental theorem of calculus part 1, because you're differentiating that integral function. In this case, it checked if you could do the chain rule when you differentiate an integral function. Like there's a really, I think, very common question format, which is why I gave you like a bunch of practice on it, and why it makes it onto my test also, the same kind of question format. How you guys feeling otherwise? It's okay? Is things like coming together now in this chapter after we've had, I know that me being gone for the first couple of lessons was like a lot, but you're seeing that like, okay, so that was just kind of the background of what we're actually going to be doing, and what we're actually doing, when we do integrals is not limits of sums at all, right? Like that's not what we're doing, but it's conceptually what we're doing. But the how of what we're doing rather than is just antiderivatives, really, which it seemed like you guys felt pretty good about. The exam stuff on antiderivatives tended to go quite well for people. So does it feel okay? We're doing all right? We'll do U sub next time. That's a integration technique to anti-differentiate something that was the result of a chain rule. So it's how you go backwards via chain rule. And then next chapter we'll start. We're going to do some applications, like some kind of application problems we can use integrals to do. Depending on how good of a three-dimensional imagination you have, that can be very easy or it can be a little bit challenging. But if you can picture three-dimensional objects in your mind, that helps a little bit. So if you're like 3D creative, if you're a spatial person, it makes things a little bit easier there. If not, it's totally doable without that, but the learning curve's a little steeper there. Then we'll do some differential equation pieces. And then I'll end up by looking at some of these other integration techniques and like when you would want to apply them. And I may sneak here and there, I might sneak some of these guys in, like scatter some of these guys into, like test 6 or test 7. Just kind of depending on when I kind of need them. Yeah, Michael.
How long are we going to have study for the AP test?
So last year, and we're going at a similar speed, I think I had like a week and a half of class days left. And then I think after you guys were dismissed, there was still another week before the AP exam. I haven't checked on the AP exam date because I don't know when you guys are done yet either, when your last day of classes is for sure, to look at that. But we'll have, I should have several class periods at the end of the year to where just like, here's a practice test, we're going to do it and then go over it. Or here's a section of a practice test. We can't do the whole thing. We don't have like a 6-hour setting to do that or whatever it takes. I mean, it's not 6 hours, but it would be to do it and go through it. It would be 6 hours. So we're going to, continue kind of on that pattern. I think that works out okay. I think it's nice to like sit down on a timed test and get a feel for like, woof, that was hard, and that's okay. And scoring it out and being like, okay, that's what you would have, like what'd we get? Kind of trying to score those similarly. So we'll also include a couple of things this semester that are not on the AB calculus exam, but I think are like things that I would expect that you'll want to have seen before you take a, like your second year college calculus course, that are pretty standard things that I think are nice to have seen before. But I'll let you know in advance that like, hey, we're doing something that like, the AP doesn't expect you to be able to do, but I do, because I think doing a good job in the class means we have to do some of these other things that I think are technically BC topics, but I think are pretty standard, first or second year calculus problems. And I'll let you know when we get to those things. Don't make the face. It's not so bad. So in general, most students find that like doing integration problems is easier than like your worst differentiation problems. Like the amount of like, things layered on top of, like multiple layered chain and product and derivative or quotient rule problems, like can be kind of a nightmare as far as derivatives go. And integration, we can't do the same amount of layering. And the reason is that fundamentally integration is the harder thing to do. In fact, there's integrals that you can write that like, there's not a way to algebraically do this. So in fact, like a whole branch of statistics is built around like, how do I do these kind of integral problems? Like, how do I build out a technique where I can get an answer for these kind of integral problems that I can't actually integrate? So like computational methods. So those of you who've done statistics, anybody in AP Stat right now? No? Anybody done like a well, Nate's done statistics from a little bit of stat from the IBSL course. So is Maria. So Maria, you know how like we do like in chapter 12 where we're doing like the probabilities for those normal curves? You're actually doing, the calculator's doing an integral there. And now that's an integral that's doable, but it's terrifically difficult. But there's other problems where it's just like there's no closed form antiderivative for this to integrate it. So in general, like integration is the harder one than derivatives, because after you've learned your derivative rules and like the chain product quotient rules, you can kind of differentiate anything. Nothing can be nasty, but like you can kind of do anything. Integrals, like once we've learned our integral techniques, you still can't really integrate anything. So, but in general, students find the integration easier than the derivatives, mostly because you can't, like things can't get as gross. But selecting the method maybe that you're going to use becomes harder. But the actual algebra usually is easier. So anyways, that's kind of where things are headed here. So yeah, you guys feel okay in general? Notice that on the test format that I gave you, the biggest single topic is like, can you do these integrals, right? Like if I give you an integral, can you do it? So like, do you need to know those anti-differentiation rules? Oh my God, yes. Like if you don't have those memorized, you know, like you're ill-prepared. Everybody's okay? So just trying to give an advance warning that if those are still kind of like, I know a lot of them, you really want to know all of them. So if you're still if you're a little shaky or rusty on those, make sure you take some time here before the test and kind of get caught up. The plan next week, we're going to do section 5.5. We'll take a review day, and then we'll be doing the test the following week. That all sound okay? Not too rushed? No big test conflict yet that you know of anyway? Okay. Cool. Who's excited